Ladies and gentlemen, on behalf of the Student Association of Energy, I would like to welcome you on the first lecture of the Donát Bánki Memorial Semester, which is held about nuclear waste treatment and recycling. It's a special honor to me to introduce you Mr. Henri Zaccaï, today's presenter. Mr. Zaccaï graduated in 1973 from Brussels University École Polytechnique in civil engineering, section physics. He was also graduated in business management in 1978 and in corporate financing in 1984. He started his career in 1973 as research assistant in Brussels University in plasma physics. He then decided to work within Treathment and then Synatom, where he dealt with all aspects of the nuclear fuel cycle in Belgium. In 1983, he joined the newly created Belgian waste agency called UNDRA, where he contributed to its development from 1983 to 1993 in the field of contractual and financial management. From 1993 onwards, he joined Areva, where he occupied various positions in international development, like engineering projects in the nuclear fuel cycle, marketing, nuclear fuel cycle activities, and so on. He now works as Vice President Business Development, Useful Recycling Solutions of the backend business. The lecture is going to be 75 minutes long. At the end, we ensure the time for questions. I would like to ask you not to interrupt the lecture with your questions. Furthermore, I would like to ask you to switch your mobile phones off, please. I respectfully ask Mr. Zaccaï to give his lecture.
Thank you very much for these kind words. Apparently it works. You estet mindenkinek. That's all what I can say, and I'm very pleased to be here with you and to spend 1 hour and a half to talk about all what's related to the spent fuel management and recycling. So, the presentation will be organized into 3 parts. First, we will give an overview of the worldwide market in terms of used fuel management. Then we will concentrate on the industrial solutions that are available on the market, especially from my company, on the used fuel management aspects, because it's a complex process, you will see. And third, we'll give some overview on the future. You are very numerous in this room, and I really thank you for the interest you give into this topic. So, overview of the fuel market. So, I think this, do you see well? Yes? Is it clear? Yes. So, this slide is very important. Why is it very important? Because one of the criticism that the public gives to the, sometimes to the nuclear energy, one of the criticism is the waste. And this chart shows that today, each year, you have, roughly speaking, you certainly know that, you have, roughly speaking, 400 nuclear power reactors which produce electricity, and you have another 400 or 500 of research reactors I will not talk of today. I will only concentrate on fuel coming out from a reactor. So you see here that 6,000 used fuel are discharged from the 400 reactors worldwide each year. So for whom, I don't know what is the level of knowledge of in the room of the nuclear power, but what does that mean? When you want to use a nuclear power reactor, what do? You take uranium and you have a lot of industrial service to prepare the uranium, to put it in a long, what we call a fuel assembly. And this fuel assembly is loaded into the reactor, and this assembly stays into the reactor roughly 4 years. 4 years, today. And after 4 years, the fuel assembly has burned all the uranium available to produce the heat through the fission reaction chain into the vessel. And after 4 years, let's say the fuel is burned. It does not produce anymore the calorifical power that you need to keep the reaction going. So you take out the fuel from the reactor. It's the same overall apparency, but it's, of course, radioactive, very heavily radioactive, and it also you have power, thermal power out of this. So what you have here is 6,000 tons of this spent fuel is discharged from reactor. Today, let's say, 2013, and you see here from where it comes. The blue is North America, the green is Europe, Russia in red, and CS and Hungary is in the red, and well, in the red, no, I think in the green, sorry. So, and Asia in blue. So, in 2030, and I will tell you then what we do with this fuel. In 2030, you see that the evolution in North America is very low. In Europe, same. Russia substantially increased, but the main increase is in Asia, of course, because of China, South Korea, Japan. This is another story, you know. But mainly mainland China and still South Korea. And today, you have this as the stockpile, so 250,000 of used fuel which are stored today into the, in a way, we will see either in the reactor pool or in dry conditions. And then this stockpile, due to this yearly discharge, will increase by almost 70% 2030. So what are the risks related to that? First of all, when you have used fuel, you have inside the used fuel uranium, which is burnt, and you have plutonium. Plutonium, which is half-life of 25,000 years. As you know, plutonium was present in the Earth about billions of years ago, but there is no more natural plutonium. Plutonium is created into the chain reaction. So you have non-proliferation concerns. Nuclear safety, obviously, when you handle this kind of material, you need to have it, as all in nuclear, be safely managed. Due to the amount of fuel, you have environmental impact and footprint. And last but not least is public acceptance. So you need to say to the public, it's safely managed, it's there, but I safely manage it. Now, if you are a nuclear operator, like MVM in Hungary, what are your concerns? Your concerns is that you want to increase your energy independence because you have uranium and plutonium into the fuel. You want to optimize your cost of electricity. As an operator, you need to do that. preserve natural resources by less uranium if you want to recycle the spent fuel, and you want to minimize the waste generated. That's the cost. So the conclusion of this slide is what? Optimizing the fuel cycle will become even more crucial to ensure sustainable growth of nuclear energy. And keep in mind that if you want to ensure sustainable growth of nuclear energy, managing the spent fuel is in the center of the concern. And you have taken in Hungary a decision is to continue in the nuclear power for with the new plants that have been decided to be built. Now, this gives you an overview of the programs of what we call the Deep Geological Repository. So I need to explain, to levelize our knowledge between you and us, what is the Deep Geological Repository. Keep in mind the following. It's very simple. In a nuclear power plant, you have two types of waste which are generated. One that we call the operational waste, which are related to the operation of the plant. It's no waste coming out of the reactor vessel. It's the operational waste for the liquid circuit I would say management. You have some filters which are slightly contaminated. You have gloves. You have whatever technological waste you use into the reactor. And these are called low-level waste, mainly contaminated with cesium and strontium with a half-life of 30 years, mainly. And this operational waste today in many countries, I think in Hungary, I think they have a shallow land repository in Hungary. Yes? So this is managed because these wastes are conditioned and stored above the ground in dedicated places. And many countries in Europe, they have that. So this is under control today in practically all the countries. What comes out from the vessel, that is to say, from the place where the uranium has been burned to produce, to have the reaction chain, and then what is discharged from the reactor at the end, this is so-called high-level waste. And we are talking of this. Today, to give you a rough, taking my watch to be sure that I'm not to talk too much. Roughly speaking, today, the only way of managing this high-level waste is to put these waste into geological disposal. Worldwide, you have three kinds of geological disposal. You have granite, you have salt, and you have clay. Why are we talking of salt, clay, or granite? It's because when you put the waste into the ground, you ensure that the stability over 100,000 years or 1,000,000 years is ensured by the geological layer. And these three geological layers, the enemy of a geological layer is water. You have no water flow into clay, no water flow in salt, because you have salt, and no water flow in granite. So today, each country has a program. But you see that the program here, you see here, let's say this is Belgium. They started license to build, start operation in 2047, and this program is under discussion. In France, 2017, we will start, hopefully in 2026, to the industrial operation. In Japan, they will start license to build and expect to start operation in 2036. In Switzerland, it's 2060. In United States, where they have today around 80,000 tons They started in 2008, and now, today, start operation, but this project has been stopped by Obama. This is the famous Yucca Mountain project, maybe some of you know. In Sweden, they are quite on track. So in 2033, application submitted, main criticality safety issues to be solved. Yes, because you have spent fuel into the ground. When you have spent fuel into the ground, the safety authorities, which allows you to operate and to design and operate, says, I want you to demonstrate that in 1,000 years, 2,000 years, 10,000 years, when all what's related to the protection of the spent fuel has disappeared, prove me that you will not have a criticality with this spent fuel. So this is the main issue. But what is the message behind that? Is you see that, first of all, no project today is implemented, industrially speaking. Second, you see the time frame here. We are speaking 230, 240, 250. So it's a very long time frame. So what the message is, it's a very scarce resource to bury spent fuel or high-level waste into the ground. This gives you an overview of what, yes, by the way, you have 3 countries worldwide which have, I would say, a planning on track, maybe not on track because it's quite difficult, but at least a planning, a schedule. And these 3 countries are Sweden, Finland, and France. And we all expect to have this high-level waste repository planned in the year 2025 in the 3 countries. So you see here overview of, this is the ground facilities. You have an oblique pit here to put the waste into the layer which is 500 meters below the surface. And here you have the galleries where you will store the high-level waste. Because in France, we will store high-level waste and not spent fuel. So, okay. Now, when I spoke of this used fuel coming out of the reactor after 4 years, what do we do with this spent fuel? So today, you have to keep in mind the people who are working into this industry, they have 2 models. One model which is the so-called once through. I will give you some details on that. And the second model is recycling. So, what does it mean? Here is the spent fuel, which is used after 4 years into the reactor. So, some countries consider this to be a waste. So, a waste. You put it somewhere, you wait, and then you will dispose it in a repository as we have just seen. But it creates a number of concerns for these countries, and we will come to that. For other countries, you have recycling, or let's say, first you have 2 steps in recycling. You have treatment, and then you have something which is called mixed oxide fuel with the plutonium. But I will come back to that. So let's see the once through. When you have your fuel, so you see this is a garbage can, a waste. You put it, by the way, in this, I have not explained you what is in this spent fuel. One is discharge. It's 96% uranium and plutonium. Let's say 94% uranium still, 2% plutonium, and 4% waste. So you have only 4% waste inside this. So you put it into a pool, and then, well, pool, which is a wet storage, what we call a wet storage, and a dry storage here. And in Paksh, for instance, you have decided to store it in pool for cooling, and then you send it to the dry storage facility, which is a vault facility. And this works to store the waste, to store the spent fuel, which is the waste. And then when you need to send it to some kind of repository, you need to do something with this. You need to package it, to condition it. You need, yes, to condition this waste. Today, this step, this industrial step, does not exist nowhere. Nobody has today a facility which conditions the spent fuel to put it into a storage, which is a disposal, final disposal. The only country today, two countries which are working on this are Sweden and Finland, which is conditioning in a copper canister, but they have very much concern with the criticality, as I just explained, so we don't have any facility today here. So this is what we call the once-through cycle, direct disposal. The recycling route is you have some facility which we call reprocessing, and I will come back to what is reprocessing. And then you separate actually the uranium, plutonium, and the waste. So you recycle, and I will come back also to the recycling concept, because out of the plutonium and the uranium that you have, you fabricate again fuel, which are loaded into a reactor. And I will come back to the concept of which kind of reactor. But what you have here is universal, what we call universal canister, and I will come back to the characteristic of this canister. And then this canister is only waste. You have only waste. This is 4% of this. And it's stored today. This you see a picture of a facility which is built in the Netherlands, and which is designed to store this kind of canister for at least 100 years. We have built this facility, and we have a demonstration of the stability of this material into this. When a final disposal will be available, it will be this canister will be stored into the final disposal. The advantage is the stability on the long term of this, and and you have divided the volume by 5 compared to this, and you have also reduced the toxicity by 10. Why have you reduced the toxicity by 10? For a simple reason, because you have taken out uranium and plutonium. And uranium and plutonium is what we call the major actinide. If you look at your Mendeleev table, you will see what is major actinide, certainly better than I do. So I continue. So this is a quite interesting curve. So you see here the comparison between the direct disposal and the reduction by 5 of the volume for the waste. So you divide the volume by 5, you have a stability of the result canister, you divide the toxicity by 10, you have a standardized type of canister. You don't have any IEA control. Yeah, for who doesn't know what IEA, International Atomic Energy Agency in Vienna, you have the so-called safeguards department in the IEA, and the job of this safeguards department is to follow for each department, each country, to follow the management of any fissile material, which is uranium and plutonium. So spent fuel, you contain uranium and plutonium, and the fact that you have plutonium leads to the control of IEA. Of course, in the case of vitrified waste, you don't have any control. And we think that you have increased public acceptance. Now, what does this curve show? Here, in red, you have the level of uranium mine. And here you have, if you don't see, you have logarithmically 100, 1,000, 10,000, 100,000, and 1 million years. And this is spent fuel. So this is decrease in activity, toxicity. This is the reduced, which is approximately the same, but toxicity of the spent fuel. And this, it crosses the curve of the uranium mine, which is a natural uranium mine, in approximately 500,000 years. If you take out the minor actinides, the major actinides, which are plutonium and uranium, this is the curve of the radiotoxicity of the remaining waste, and it crossed the curve of the uranium approximately here at 10,000 years. So you have reduced by a factor of 50 the time of the radiotoxicity to the environment. And this curve is when you take out what they call the minor actinides, which are neptunium, curium, and americium, contained in the waste. But this blue curve, which is the reprocessing of the spent fuel, is working industrially. In France and in some countries, they have tried to take out the minor actinides. It's possible, technically speaking, but we don't go this route because the economics are not there. And of course, you have reduced dramatically the toxicity because after approximately 200 years, 300 years, you have something which has decreased in terms of radiotoxicity to the level of uranium mine. But what do you do with the neptunium, americium, and curium? So this is another story. That's why today this is not industrially implemented. So the conclusion here, optimization of transportation resources, storage facility, and repository is something that you manage through the recycling route. Okay, now some overall picture. Okay. This is the way many countries are looking at the way they manage their spent fuel. So here, officially, only 2 countries has made an industrial option for direct disposal, which is Finland and Sweden. These countries are looking to recycling officially. China is looking at recycling, it's announced. France, we are doing this in our facilities. Japan, they have a facility. Russia is doing it. India is doing it. And the Netherlands is implementing this recycling route. These countries have, some of them, done reprocessing, recycling, but still it's under discussion. They are not yet in a position where the policy is defined. Well, let's do some, I would say, promotion of Areva. So this is France, where you have the facilities related to the backend. So the facilities which we are dealing with today is in La Hague and Melox, the orange one. The other facility I will not speak of because this is other facilities related to the backend, which are decommissioning, waste management. I will speak only of La Hague and Melox. What do we do in La Hague? In La Hague, we reprocess the used fuel. And I will give some views on what industrially it means. And Melox is the facility where we produce the recycling of the plutonium into a new fuel. As we do in Roman, we use, this is a front end, what we call the front end, where we fabricate fuel, but also exactly only with uranium. Here in Melox, we fabricate fuel with plutonium recovered from the reprocessing. So this gives you an overview of what EDF is doing and what means the I would say, the classical way of managing the used fuel. What does it mean, the classical way of managing the used fuel? So you have the power plant. The power plant discharges the fuel. For instance, in France, EDF is recycling approximately 1,000 tons per year, which contains 1% plutonium per ton. And this is sent to our facility for recycling and MOX production, the two facilities we have just seen. So here we have the recycling of the valuable material, which are plutonium and uranium. And this, here, you have the plutonium, which is fed into the recycled fuel at a level of 120 tons per year of fuel now, is sent back to the nuclear power plants in France. In France, you have 58 power plants, and among these 58, you have 22 which are loaded with MOX. And here, the so-called ultimate residues, the vitrified waste, you have vitrified and compacted waste, and I will say a word on how we get this waste, are sent to the customer back because we, as an industrial player, we are not owner of the waste. We have to send back the waste to the customer as we send back the waste, the uranium and plutonium. So this is the classical way of recycling the spent fuel. So this gives you all the capabilities that we have in Areva, as we just have just seen recycling the reprocessed in La Hague. We have some facilities where we do dry storage, wet storage, and we have also facilities to transport not only the spent fuel but also the waste. So we try to have here a combination of all these technologies. Now, what is reprocessing? Let's concentrate on what is reprocessing. So you have three important steps. First, you take the spent fuel, which is 4 meters long. It's 4 meters long, approximately, fuel. So you cut the spent fuel and you dissolve it in oxide. We will see the process. Then you extract and separate the uranium and plutonium, and you condition the final waste. Okay, so here you have the process diagram for the so-called reprocessing. First, you have here the canister, what we call a cask, in which you have something like, depends, between 20 and 12 and 20 spent fuel, which are the transport mean from the power plant to the La Hague plant. Then you have what we call the dry unloading, and we have also a wet unloading. So do we see something here? Yeah, here you have, once it's unloaded from the cask, here this is 4 meters long, it's unloaded, it goes on into the pool storage. Here you have the pool, which is in La Hague. Then what do we do after that? You take it stays, well, depending on the way we manage the fuel into the plant, because it's industrial management of the waste, of the spent fuel, sorry. Then what you do, you cut. It goes into a cutting device, and you cut the spent fuel. Approximately, each time you have something like that. This is what we call the shearing machine. So you cut this, and it goes into a large wheel, something which is, the diameter of this wheel is is this high. And this is what we call the dissolver. And this, all the cut pieces, which are like this, goes into this big wheel, which distributes, and it's here, and you have a separation of, because, yes, the spent fuel is a metallic part, which is the two hand pieces, and then you have grids, and then you have a long rod, which is this kind of diameter, 10 centimeters, 10 millimeter. And in this you have pellets of uranium. And when you cut here with this shearing machine, you get small pieces of the rods. Inside you have the pellets of uranium, and then you separate the metallic part from the uranium containing waste and plutonium here, and you separate what we call the meat being uranium, plutonium, and the waste, fission products, and the hulls and end pieces. This all is the metallic part. This is compacted, stored, and you get this, what we call the universal canister, where you have compacted metallic pieces, only metallic pieces. And the uranium and plutonium, and then uranium and plutonium, what do you do? When you get this into, it's nitric acid, it's dissolved into a nitric acid solution, and this solution, you have separation from uranium, plutonium, purification, and then here the final waste, which are what we call the vitrified waste. And you get the same overall size, geometrical size of what we call the universal canister. These are waste, and the French law impose us to send this back to the customer. This is something which is under the law. And the uranium and plutonium are purified and can be recycled then into other reactors. So this is the way the process of reprocessing works. Now I will give you an overview of the other plant, process flow chart of the other plant, which is the MELOX plant, where you fabricate plutonium and MOX fuel. So the MOX, the plutonium is, you have 6 steps. First step is what I've not said is the plutonium, you have 8% of the plutonium and 92% of so-called depleted uranium. What is depleted? Who knows what's depleted uranium? This is okay, so I will give you some information on depleted uranium. But I don't have any chart on this. I will give some explanation. How much time I have? How much time I have? Okay. So when you have uranium out of the ground, it's uranium which contains 0.7% of fissile uranium, which is the isotope of U-235, and 99.3% of uranium which is not fissile, which is the U-238, 238. When you get the natural uranium, when you look at the neutronic of the core, it's not enough to have an adequate, I would say, fission reaction. So you need to enrich the uranium, natural uranium, with fissile uranium, which is uranium-235. How do you do that? Well, you do that by having an operation which is called enrichment. I will not enter into detail. For whom who are interested, I will give some information because it will be too long, but you enriched. What does it mean? Is that you take, let's say, 100 kilo of uranium, natural uranium, you put this in a plant which is called an enrichment plant, and what do you get out of it? You get, because you don't lose uranium, when you get after the enrichment process, you have, let's say, depending on the enrichment rate, but you have simple figures, you have 80 kilo of depleted uranium with a uranium content which is around uranium fissile material around 0.2, 0.3%, 80 kilo, and 20 kilo with enriched uranium. It is to say, uranium with 4% content of uranium-235. Have you understood what I have just said? Good. So what it means is that you have 80 kilo of uranium, which is left today. It's a material called depleted uranium with a content of fissile material, 235, of 0.2, 0.3%. You have plenty of it around the world. So, the way we are fabricating MOX is that we mix approximately per pellet, we mix 8% of plutonium and 92% of depleted uranium to get that's why it's called mixed oxide fuel. Mixed because it's uranium, depleted, and plutonium. So the process that we have in Melox is you create here the pressing and pelletizing. You get the pellets as you have put into the rod. You sinter the pellets, then you grind to make it uniform, and then you fill the pellets into the rod, and this is a final rod, and this rod composes the final assembly where you have, depending, it's 14 times 14, 14 times 14, or 150 or 200 approximately rods like that into a final fuel assembly. And just to give you a rough idea, one MOX fuel assembly have the power of 1 year of electricity for a city with 70,000 inhabitants. And usually in a core, well, whatever MOX or not MOX, you have 150 to 200 fuel assembly in a core. Okay, so this gives you an overview of our facilities in France, Areva. We have reprocessed 30,000 tons. 30,000 tons, let's to keep in mind, today you have 6,000 tons which are discharged, first charge, you remember, 6,000 tons which are discharged per year, and approximately 20% of this 6,000 tons are reprocessed worldwide. Some in France, many in France, in Russia you have also, in UK you have, and tomorrow it will start in Japan. So, but we have reprocessed in this facility, and here you have the curve of the production with our because we had three plants in La Hague. The first plant, which UP2400, which is today under a decommissioning state. Then you have the UP2800, which was a plant devoted to the French customer, and the blue one, which is UP3, which is a plant devoted to the foreign customer. But today we have mastered these two plants to have a uniform, united industrial platform. So originally it was like that, but today it's a unified platform. So this is you see we started in 1980 approximately, and we are continuing to reprocess each year approximately 1,200 tons in La Hague. And all is our customer, France, Spain, Australia, yes, we have reprocessed research reactor. Fuel from Australia, Japan, Germany, Belgium, France, Netherlands, Switzerland, and Italy. And Melox plant, we have produced 2,000 tons of MOX fuel as of 2012. So today what we can say, and here is the production of the MOX plus the reprocessed uranium. And so recycling today is a fully industrialized process. Okay, it's a bit a complicated chart, but if you can see it, this is something new to us for our customers. So you remember the first chart where you had the recycling of EDF fuel. So here you have an interesting concept which is pre-cycling, and another interesting concept which is global recycling service, and we have another concept which we have been discussing with damaged fuel. I will not get into the damaged fuel because sometimes you have damaged fuel, and we have some solutions for that, but I will not enter into this. So let's look at this, what we call pre-cycling. What is the story around pre-cycling? You had a customer who said, I want to reprocess my fuel, and I want to recycle plutonium in my reactor. But when you stop the reactor, and this plant will stop in 2033, I don't want to have fuel to manage with plutonium. So, because at the end of the lifetime of this plant, he will discharge MOX fuel with plutonium. And he wants to recover all the plutonium. But since the plant is shut down, how can he use plutonium since it's the end of the lifetime of the plant? So he had a concern, he had a problem, this operator. So what we said to this operator, okay, we will lend you plutonium, we'll advance you plutonium, and when we will recover the last fuel from at the end of the lifetime of the plant, we will reimburse ourselves with the plutonium we will recover after reprocessing. And that's what you are looking. We advance plutonium, we fabricate the MOX, it's burned into the reactor, the used fuel is sent back to Areva, and the last load with the used MOX is recycled reprocessed by Areva, and we reimburse ourselves with the plutonium we recover from the reprocessing. And this customer will receive only the vitrified and compacted waste, which we have just shown you. And this will be, so no spent fuel, only canisters of vitrified and compacted waste. So he's happy. So here you have another story, which is the global recycling service, and this is a customer who say, okay, I want to get rid of my used fuel, and I don't want to recycle plutonium. Many reasons. Not interested. So, okay. So we say, what we propose you is we take your fuel, we reprocess the fuel in La Hague, we send you only the vitrified waste, and the plutonium, we keep it. And we recycle this plutonium in another operator. We have done this with a customer in Italy. He has 300 tons of used fuel. We receive the used fuel, we reprocess the used fuel, we keep the plutonium, and the plutonium will be recycled under MOX 4 into another reactor. So you see all possibilities are there to use this industrial platform. And this gives you an overview. Well, we have just spoken of the canister. This canister is this height and approximately this diameter, and it's fully stable, and it's stored in this kind of building today in the Netherlands. This is the way it comes from the vitrification, and here you have molten glass, which are this molten glass gets into this, and it's solidified. It gets solidified into this, and you have a stable vitrified glass. And this kind of waste is, the specification is accepted in all these countries: Netherlands, Belgium, France, Spain, Switzerland, Germany, Italy, Australia, Japan. Well, I will not spend much time with this, but this gives you a rough overview of all the operations around the used fuel, storage. Here you have storage, indoor storage, vault system. By the way, in PAX you have the vault system. Wet concept, which is the storage in a pool. And all these are different types of storage of fuel into dry conditions. There is one concern which is not shown into this picture, this slide, is that when you store the used fuel, you have to say, is a living body. It's a living organism. You have you have power, thermal power getting out of it, and you have radiation. So there is a continuous activity, and you have a modification of the physical behavior and chemical behavior of the material. And there are some concerns today. When you have, in wet storage, it's not a problem because you monitor the evolution, the behavior, mechanical and chemical behavior of your used fuel. But when it's stored here into dry condition, into this, you see this kind, it's casks or canisters here, concrete overpack. You don't know what's going on. You have it's dry. It's you cannot. You have a protection for the thermal and radiation, and at the end of the day, you don't know what's going on. So there are a lot of study today in the United States, in particular, to look at the way after 10 years, 20 years, 30, 40 years, what is the behavior of this kind of fuel, and the behavior of this fuel can be a bit more complicated to monitor if you increase the burn-up. The burn-up, the burn-up is the way you have burned the uranium through the fission product into the reactor. And at the end of the day, it's as you have ashes compared to ashes, but you have taken all the energy out, and now the operators are willing to have more and more increased burn-up. And this could create more concerns in the behavior on the long term of this spent fuel. Future overlook. Okay. Before I go, can I show the movie? Then we will come back to the future outlook. It's a 5-minute movie, you will see, to give you some explanation on, I hope, quite funny way to explain the different way of managing the used fuel, if my colleague succeeds.
Bound for treatment, please board at gate 8.
Boy, the news sure isn't very good, is it? At least we can say we've done our job. No one can blame us for all these weird climate changes. And we're not even through working. One-way ticket, huh? Yeah, my boss is retiring me. But I'm not ready to retire. I still got lots of energy. I'm sure glad my career isn't over. Oh, you're in the closed cycle, huh? Lucky you. I guess your boss can afford it. Mine could never send me there. Oh, no, you've got it all wrong. Take a closer look at our tickets. Hey, they're practically the same price. You got it. Plus, there are all kinds of benefits. For example, I'll end up supplying 30% more energy. Just think what that means for global energy reserves. And with 30% more energy, my boss wouldn't need to rely on others so much. Exactly. The closed cycle is the wave of the future. But my future is being watched 24 hours a day for years to come. My boss looked into this. Too cumbersome. By treating me and recycling me into MOX fuel, there is less waste to watch after, and for a shorter period of time, too. It's true. It's pretty hard to use me any other way, especially in a bad way. You know, with MOX, you can get rid of nuclear materials from dismantled weapons, and you can even get energy in the process. I'm sure my boss will be really interested in all of this. In fact, I'm going to call him right now. By the way, who does your boss work for? Welcome to the mysterious Enigma game. Here are 3 clues for our candidate. First clue, they've successfully treated and recycled for 25 years. Second clue, their facilities operate around the clock. Third clue, safety and environmental protection are among their highest priorities. Well, does our candidate know the answer? The back-end division of Areva? Plus, with Areva, my boss knows the schedule will be met, but most of all, he knows they'll deliver what they promise. And just between us, okay? With Areva, my boss doesn't even have to lift a finger. What do you mean? Not only do they take care of the treatment and recycling, they handle all the logistics. Oh, you mean like transportation? Yeah, but it's more than that. First, you have to make super-duper casks to put the nuclear fuel into. Take me, for example. I'll be taking care of my whole life by Areva's back-end division. But it doesn't stop there. The day my company's facility is ready to shut down, the back-end division will still be there to take care of things. Okay, now I'm really going to call my boss. Hello, boss. The reason I'm calling you is... Okay, boss. See you later. Well, what does he think? Oh, he's really interested, but he needs to know more on how Areva works. That's easy. At Areva, they know how to adapt to any situation.
Like me, for example. I was kind of in your situation, and the back-end division made a great offer. They had me hibernate for a while, like an old grizzly bear, till I could come back.
Yeah, they found the best solution for me too. They bring me directly to them and take care of me until I go back to work.
Hello, how y'all doing? It was the opposite for me. My boss wanted everything done in our country. So engineers from Areva back-end division worked with him and helped him build a treatment plant over there. And then they trained him how to use it.
You see, they always find the right solution. And if your boss thinks he's not ready, tell him not to worry. They'll never leave him in the lurch. They keep a close eye on things, and they're always there as soon as they're needed.
Now boarding all gases bound for treatment at Gate 8. All aboard!
I've got to go. Hope I'll see you around. Guess what? My boss has finally agreed to let me go with you.
Okay, so back to the future now, looking at the future. So I would like to have the other slide. Yes. Yeah, thank you. Okay. Now, looking a bit into the future. Today, for your information, we have what we call as 400 nuclear power plant in operation. You have generation 3. What does it mean, generation 3? So, to give you a rough idea, you have generation 1, which was built into the 50s, 60s, generation 2, which are stabilized stabilized technology. First, you have generation 1 with gas graphite in some countries. Okay, generation 2, and then we had generation 3, which is the same kind of technology. This is to say, with uranium, you have the fissile reaction, which is with low neutrons. And proposition of generation 4, which are fast neutrons. So you have moderator to lower the speed of the neutron for the fissile reaction, and then you have to transport and to cool in the vessel, you have a moderator, which is today pressurized water. For instance, in packs, you have pressurized water. In pressurized water, you have water is the neutron, for moderator, and for the transport of the power. Now, this is generation 2, and generation 3 is what? When we had Chernobyl, the decision was taken to have never that again, and then zero risk in terms of accident condition. In accident condition, nothing could be out of the plant to affect the man or the environment. So this is generation 3, which you have now being built worldwide. But you don't change the basic technology, which is PWR or BWR. What is generation 4? Generation 4 is a future reactor. You had some built worldwide, very few, where you do not need to have, let's say, a moderator to lower the neutron, but you have fast neutron. This is the so-called fast neutron power plant, and this fast neutron power plant, you have today 6 generation 4 technology which are being looked at, but this is fed with plutonium. It burns plutonium, any plutonium. So this is the so-called generation 4. So today you have the light water reactor. You used UX discharged from the power plant, and then direct disposal is final waste. Sometimes, as we just explained, you, instead of consider this as a waste, you reprocess. When you reprocess, you produce MOX, just explained, and you burn MOX into the light water reactor. And you produce used MOX. And then this MOX is stored into a pool. Now, you have to know that used MOX, if you want to continue to do the cycle, you have some isotopes of the plutonium which lower the efficiency of, if you want to again recycle, you have a lower efficiency of the plutonium content. Then, here, I've just mentioned, I explained depleted uranium to produce the MOX with the plutonium. Now, the story with generation 4, this is the future outlook, is that you, you see here, you have the used MOX, which is sent to the reprocessing, and the plutonium out of this reprocessing does not go to generation 3, light water reactor, but it goes, this is the red arrow, it goes to the fast reactor. Because fast reactor, they are much more in terms of reactivity, much more, they don't care about the plutonium content. They burn all, with the same efficiency, they burn all plutonium. Because, and you have used fuel out of the fast reactor, and you store it in pool. Then what do you do after that? You send this to the recycling plant, and you are here in a situation where you are into a stable situation, where you can reprocess, produce MOX, send to the fast reactor, and you are a real cycle here. And I will not enter into detail, but here you have a maximized nuclear system. Here you have MOX, but you cannot continue to use MOX into the cycle again. You need the fast reactor to enter into a stable system. You maximize the nuclear system performance, you handle the used nuclear fuel, you increase your natural resource because, of course, as you can imagine, you don't use uranium from the ground because you have plutonium going around to be burned many times. And you have energy independence. You don't buy much uranium as in generation 3, and you have a fleet performance. So at the end of the day, the future outlook where you have the MOX today, which is burned into generation 3, tomorrow the used MOX and the MOX into a cycle will be burned into a generation 4 reactor. Okay, this is the stability final stage where you have this, and you can also continue to use one cycle into generation 3, but the result of the used MOX will go into the recycling of generation 4. I hope that it is clear. Sorry, I have asked to ask you again for the last chart. Not too late. It's one last slide, huh? And then questions. The last one. Okay. No, this is not the last one. Yeah, no, the next one. Sorry, this one. So this gives you an overview of the industrial situation of what we have just explained in many countries. So let's start with France. Let's start with France. So in France, generation 4, generation 3, you have the La Hague. Do you see from the La Hague plant, Melox plant, we have just explained. We have generation 4 program, which is the Astrid reactor. This is an ongoing program under the French Atomic Energy Commission management. And this is to prepare the generation 4 in France. And we have plans, of course, to build fabrication and treatment of the generation 4 reactor. So we have industrial base today to prepare the generation 4. This is the future outlook in France. In Russia, they have the Mayak plant, which is for reprocessing. They have plans to build another plant in Krasnoyarsk with the increased capacity and a MOX plant. Okay. I have not seen the MOX plant today, but they expect to build a MOX plant. And they have started the BN800, which is a fast reactor for generation 4. China, they are looking for building a recycling plant, and they have ambition to build recycling facilities, and they have also ambition to build generation 4 reactors. Japan, they have the Rokashomura, which is a transfer of technology from the La Hague plant to Rokasho in Japan. This is a reprocessing plant. They have plans to build what they call GMOX, Japanese MOX, and they have also, well, it's a bit more difficult in Japan, they have the Monju fast reactor for the generation 4. South Korea, they're looking for reprocessing. In India, they have their own program. You know that India has not signed the non-proliferation treaty. It means that today India is a bit closed country when it comes to the management of uranium and plutonium. So, but they are building their own program without cooperation with foreign countries or foreign companies because they have not signed the non-proliferation treaty. And United States is not working much into today looking at Generation 4 reactor, and we are building today with a US company a MOX plant. This is an interesting topic. We are building a MOX plant. As you know, in the 90s, there was this plan to lower the bombs in Russia and United States. So there was a disarmament, decommissioning of a number of nuclear bombs. They got plutonium out of it. And that's what the excess plutonium, about 54 tons of plutonium. And this plant in United States is bound to use 36 tons out of this plutonium in excess to produce MOX to feed civil reactors in the United States. So I hope that this gives you, a United Kingdom, of course, they have MOX out of, they have plutonium stockpile, and they consider fast reactor as well. But you see that I would say the 4 countries which are even five countries which are most advanced into Generation 3 and tomorrow Generation 4 is France, Russia, China, Japan, and India. So this, I will not have seen that, and I would like to thank you for your attention.
I would like to thank you, the lecturer, and now we have the opportunity to stand our questions. So, who will be the first? I hope that only the first one will be so tough. So.
Yeah, maybe I could ask myself one question so it would, you know.
I have the first question. Could you go back to the figure where you had the fast reactor in your sketch? So the other one, previous one. Go back.
But this is another presentation.
Okay.
But I will. The one with the evolution of the, that's what you want to see?
Where you have the light nuclear reactors, the MOX, and the fast reactor at the top.
Yes. So, you can take any. Yes.
Yes, this one. Okay, thank you very much. So you have some numbers in the figure. The 32, the 4, and the 1 in the brackets.
Yes.
So could you explain what are these numbers?
Well, this is just to give a figure to size. So you have 32 used MOX, UX. This, and in this scheme, you generate 4 used MOX, and then to give relative volume of the 2. This is to give a relative volume of the cycle in which you will enter. Because when you recycle your 4 used MOX, when you recycle 32, you get 4 used 4 MOX here, so 4 used MOX. And when you recycle this, you get 1 used MOX for the fast reactor in terms of relative quantity of plutonium. Yes?
Presentation. It was very funny.
I hope that you have learned something.
Very important aspect was mentioned in the cartoon. This is the economic spec, the prices of MOX and the fresh uranium. what is the situation if you compare it with future thorium reactors? What is thorium?
Thorium.
Yeah. Is there any estimation about that? What is going to be more economical to recycle, use the uranium fuel, or to use thorium?
Well, first of all, I have to say I know nothing about thorium. The only country who is managing its cycle with thorium is India. And why is India doing that? Because thorium, you have a lot of thorium around the world, you know. I'm not a geologist, but there is a lot of thorium. By the way, the nuclear community could have started to build a cycle with thorium because it's quite efficient. I know nothing about thorium, but what I do know is that it's workable. No, so I cannot give you any indication on the thorium cycle. It's a quite interesting cycle. India is implementing it because, for obvious reasons, they cannot work with other countries, and they don't have uranium, but they have thorium. So they have developed an industrial thorium cycle. But if you want to have some information, I can work after this lecture and send you some information, but I cannot answer the thorium. But in your question, you had also interesting topics about reprocessing. What is the economics of reprocessing and MOX? So, to give you, and this is a question which is really something which is at the heart of the management of each operator. What do I do? We have explained that you have two routes, and you have the possibility to recycle MOX, or not, or to consider the used fuel as a waste. Now, if you compare the two cycles, let me first give you an indication, is that there are two references that you can look at. First is OECD. OECD has issued in 2011 a study which compares the two routes and compares even the situation when you look at Generation 4. And you can even go at the, I don't know if you know, but it's on the website, it's Cour des Comptes. You know, Cour des Comptes in France is, let's say, a public body which controls all the government entities, how governmental entities in France, not nuclear, it's all, any public entities, governmental entities are behaving, do they manage well or they don't manage well. And the Cour des Comptes, they have published information on the economics of the cycle. So this, you can go, but I will not answer you. I'll try to answer you. So clearly, an operator that needs to manage its fuel, he says, okay, but it's much more economical for me, apparently, to store the waste, store the used fuel and wait 100 years, whatever. I will not spend money, I just store, etc. Yes, this is a concern because the law, generally speaking, says that in all countries that you have to put money aside to manage the spent fuel in the years to come. And you cannot say, I will give this to the future generation, wait and see. Some countries are doing this, but less and less, because there was a EU directive today that says you need to do something and to explicitly say what you are going to do. Now, when you look at the reprocessing route, yes, you have a spending which paying for the reprocessing, but at least you have some you have some certainty. But when you look at the economics, it's equal. Cash flow are not equal. Economics are equal. And I will just quote, to answer your question, I will just quote one of my customers. He said, yes, maybe I have a cash which is a bit important because I pay you for reprocess to do the work. But at least I ensure certainty of my cost. I know what it will cost me. If I go the other route, I don't have industrial facilities. I can do calculation, and you know, in nuclear, you have a budget of 10 at T0, and at T10, you have a budget as who knows. So you don't know. So you buy certainty with economics, which are quite equal when the OECD study explains that quite well. Equivalency in terms of economics, not same in terms of cash flow, obviously, because you need to pay the reprocessing at first. I've answered your question? Thank you.
Another one?
My question is also related to this graph. You explained that in the future the plutonium can be used in fast reactors, in fast breeder reactors, in fact, and that they, with these reactors, a cycle can be built up where you can produce also plutonium for the light water reactors. It's only depleted uranium is needed as an input to the cycle. On the other hand, in light water reactors, you can recycle only once because of the deterioration of the plutonium in the cycle. So my question is that isn't it a better option to wait with the recycling of plutonium while fast reactors are available? And isn't it seems a little bit like wasting some of the plutonium in the light water reactors, which uses them in a much lower efficiency, while in the fast reactors you can use it with much better efficiency?
Very good question. Thank you for that. This is a very, very good question. It's a key question. Yes, you can do that, of course. Yes, you can do that. Yes, you can say, I will put my used fuel, and I wait that I will have a better use. By the way, that's what you say, a better use of the plutonium into fast reactor. Yes, but we are into a real world. And the real world says that if you don't do things and you wait for tomorrow, you will lose the technology. Of course, recycling MOX plutonium into generation-free reactor is, I must confess, the efficiency is not as good in generation 4. But today, the companies, the countries that have built facilities to produce MOX, they have the technology. It's not an easy technology to manage. It's a real tough technology, you know. And so tough that some countries, you know, are facing difficulties to building. Now we use MOX, we gain experience in MOX, and we offer MOX to any countries that are willing to do so. And we have countries which are willing to do. So my answer to your question is, yes, it's a very important question. And yes, we need to keep the technology going, otherwise you will lose it. And you will lose the possibilities tomorrow to say, I'm going to produce fabricated MOX for the generation 4. Answer your question?
That based on this, is there any policy in France that you limit your MOX recycling in a way to keep technology, because it's quite understandable what you say about technology, but do not use too much plutonium, which will result in some problems when starting up fast reactor?
Well, this is also a very good question. The answer is the following. I will just quote you EDF policy. EDF is the main utility in France, as you know, maybe, 58 reactors. EDF reprocess the used fuel, recycle plutonium in 22 reactors out of 58, and they do not ask us to recycle used MOX, because they will store, we are storing used MOX to have these plutonium resources to be once reprocessed to be feeding the generation 4. So this is the policy of EDF. This is not Areva. This is our customers' policy.
last question.
Only last?
The chance. Yeah. Is there anybody who would like?
My question is that in what year do you expect the start of an industrial scale of the first real Generation 4 reactor in France? As far as I know, it would be sodium technology.
Yes, it's Astrid, it's sodium technology. Tough question. Eh? Well, I don't know if there is a real announcement. The CEA says that the first prototype will start in 2020. This is the official announcement. Well, prototype. Now, if you look at the industrial scale, so we are between us, don't quote me. Huh? I would say 2040, not before. And to have in deployment of industrial scale, the idea is to have both, of course, EPRs are now being built to replace the existing fleet, and then the deployment of the Generation 4 reactor on industrial scale starting in 2040.
Maybe one more because it was quite short. If anybody would like to, but don't be shy. After the end, we will have some minutes to talk personally with the lecturer, so you can do that. Now, let me thank for our lecturer, Mr. Zaccaï.
Thank you.
It was our pleasure to
My pleasure.
And please,
now I can do it, yeah?
It's a very fine.
Okay. Thank you very much. Thank you. Thank you. Thank you all.